different vibe.
Yeah.
It's like the most.
I'm not the one. Yeah, what's our point class? I just try to send it.
It's like a oh, I mean, there was a way you could have at least when I didn't do it.
This summer I might have played some solvers.
Yeah. Remember the way that was really stressed?
That's.
I think even if I get it wrong, it's only going wrong by
What else do you want to be?
Okay, good morning everyone. Good morning. Your exam is officially closed, so I will start the grading process and hope to have this exam back to you in about a week and a half. Okay, it's going to take me some time. How was the exam, by the way? Fair, long, happy for the 4 hours? I would be too. All right. Going forward, I realize that there is a homework set that is due this week, but I don't want to have anything due this week. Okay, so I'm going to have the following plan. You're going to have a total of 2 homework sets for the remaining portion of the semester. One homework set, I'll be posting it tonight or tomorrow, and it will be due next week Sunday. Okay, not this week Sunday, it will be due the next week Sunday. And then the last homework set will be due on the last day of our lecture, which is on April 25th. So that gives you about a week and a half for both the homework sets. The next homework set will focus exclusively on radiative resistance networks, and then the last set will focus on convection heat transfer. Okay? I want to solve one more problem on the resistance networks because I went a little fast towards the end of the previous problem, so I want to do some justice to it. So we'll do one more problem, and then I'll start an introduction to convection heat transfer. I'm assuming that all of you have taken fluid dynamics, but I also realize that these things don't stick in the mind that much. So I will have to go through the boundary layer theory, okay, where I go through the basic equations for boundary layer analysis, because we're going to need them for the convective heat transfer equations. All right. So hopefully by the end of class today, I'll have started boundary layer theory, explaining the basics of fluid and thermal boundary layers, and then we will take it up from there on Friday. Those equations are a little scary, the boundary layer equations. We will be doing this in 3 dimensions, okay, and then we will reduce it all into 1 dimension. All right, so we start off on a very general basis. We will look at mass conservation, which is a continuity equation. We will look at Newton's laws, which is conservation of momentum, which is the scariest of the 3 equations. The third one is conservation of energy. That's where temperature comes into play. The first 2 are basically only for fluids. Okay? It's interesting, and I have asked that as an exam question in the final exam, to take the boundary layer equations and reduce them to the form that is solvable for heat transfer. So please be prepared for that. And I will make sure that I spend enough time to tell you how that comes about. Okay? Alright. Problem. We have the following setup. It's a cylinder. So it's a cylindrical enclosure. The top surface I'm going to label it as 1. The bottom as 2. And then the sides, which is going to be surrounding these 3, will be surface 3. Okay. When I'm labeling it as 1, I'm labeling the interior of surface 1. Okay, so that's something to also note. Yeah. The temperature of 1 and 2 are given to us. So T1 is 800 Kelvin, T2 is 500 Kelvin. Epsilon 1 is 0.4. Epsilon 2 is 0.4. All of these are diffuse gray surfaces, otherwise you cannot use the resistance network idea. That's something to be wary of as well. T3 is not given to us. That's what we're supposed to find. And you're told that surface 3 is a re-radiating surface. Which essentially means that it's insulated, so there is no heat flux, net heat flux, which is coming out of surface 3. Okay, so this implies that surface 3, Q3 is equal to 0. No heat flux coming out of surface 3. And similar to what we had for the last problem that we solved on Monday, I'm given the formulae for the view factors. Okay, it's a similar formula. Oh, it's the same thing actually. Two surfaces which are separated by a height of L. Radius of the first one is Ri. This is Rj. Okay, the view factor is given by the following equation. So Fij is 1/2 S minus S square minus 4 times Rj by Ri square whole to the power 1/2. Please make sure that you are writing down the formula as presented here. It is possible that I might have put the power 1/2 on there in the last class. Okay, that's not the case. If I have made that, that's an error on my part, so this has to be the place it is written in currently. Okay, so that's something that you want to note. And S is 1 plus Rj square by Ri square. Excuse me. Okay. So let's do this problem step by step, okay, including the calculation of the view factors and so on. Okay. And T3 is not known to us, and also let us find out Q1, which is the net heat rate out of surface 1. Okay, so Q1 is net heat transfer rate. From surface 1. And T3 is the temperature of this surface. Sorry. Okay, I hope the problem is clear to everybody in terms of the details that are presented. Obviously, this problem does not have any conduction and convection because there is no mention of thermal conductivity. There is no mention of any conductive heat transfer coefficient as well. This is similar in looks to the problem we solved in the last lecture, okay, which is the ice rink, but that had too many things going on. So essentially what I'm doing in this problem is I'm focusing only on the radiative aspect of what was going on in the ice rink problem. Okay, so let's do this step by step. You always start off by drawing the resistive network. Okay, no matter what the conditions given are, you draw the general resistive network, then you start reducing the nodes and add other details. So I start off with EB at T1, J1, J3, J2, EB at T2, EB at T3. So EB, T1, T2 and T3, these are the primary nodes, okay? And then J1, J2, J3 are the secondary nodes, and we join them all by the resistances. The primary and the secondary nodes are joined by the surface resistance. So this is R1, R3, R2. These are the surface resistances. Then I have the geometric resistances which join all the secondary nodes. So between 1 and 3 I have R13 or R31. There is nothing lost in calling it either one or the other. Okay. Then I'm going to have R23 or 32, and then R12. Then I start reducing based on information that's given to me. Okay. Let's start calculating each one of these resistances. First of all, notice that Q3 is 0. So Q3, typically if there was a Q3, that would start here. Okay, if there was a Q1, that would start here, and if there was a Q2, they would always start from the primary nodes. These are all the rates of heat transfer from surfaces 1, 2 and 3. The net radiative rate of heat transfer from surfaces 1, 2 and 3. Let's look at Q3. Q3 is 0. This is a re-radiating surface, or essentially the net flux on the inner surface is 0 for 3. So this tells me that EB at T3 minus J3 divided by R3 is equal to 0, or essentially EB at T3 is equal to J3 or sigma T3 to the power 4. Okay. So I can cancel off this branch here because I know that EB at T3 is the same as J3. So this is sigma T3 to the power 4. And EB at T1, sigma T1 to the power 4, and so on. And this is sigma T2 to the power 4. I do not have any other simplifications that can be afforded to me because epsilon 1 and epsilon 2 are not equal to 1. If they were equal to 1, then I can say that the resistances R2 or R1 is equal to 0 and EB is equal to J for those nodes as well. But I can't do anything. They are not equal to 1. Okay? Alright, so then let's start calculating R1, R2 and R3. R3 is not needed, so just R1, which is 1 minus epsilon 1, epsilon 1 A1, and let's say that the radius here, I did not give the geometry, but the radius is 1 meter, and let's say that the height is 2 meters. Which we will need for the view factor. Alright, so R1, 1 minus 0.4 by 0.4 times pi r square, which is the surface area. Okay, and I have these numbers here. This is 0.4775. Units are per meter square. R2, same formula. Okay, surface resistances. 1 minus epsilon 2. Epsilon 2 A2, substitute. A2 and A1 are the same. If I do the substitution, this ends up being the same value, obviously. Epsilon 2 is also the same. Which is 0.4775 per meter square. To calculate any of these Rij's, I need the view factor. Okay, so the general formula is Rij is 1 by Ai Fij, which means I need F13, F23 and then F12. So we need F12, F13, F23, or equivalently F21, F31 and F32. No harm done if you're flipping this. as long as you flip the area as well. And we do that by making use of this formula given for the view factor. Alright, so step-by-step analysis. First, draw the resistance network. Figure out any useful information given from the problem statement. Typically, either there will be some radiating surface or maybe one of the emissivities will be equal to 1. Use that to simplify the network a little bit. Then you calculate these view factors. Sometimes they may be given to you. Sometimes we can directly calculate them using the geometry of the problem or formula will be given to us. I'm going to post a few more problems for different other types of surfaces on your carbon page, where you'll use the formula to calculate the view factor. This is just plug and chug. It is kind of tedious, but it has to be done. Okay? Alright, so F12. This is a fundamental equation that we can make use of. Then F21, F22, F23 is also equal to 1. I typically like to write these for the flat surfaces because I know that for a flat surface, that's 0. F22 is also 0. There is no harm done if you write it for the third surface too. Doesn't really make any, it's not of any much use to us. Okay. So the aim is if I can calculate F12, I can calculate F13. And likewise, F23 is 1 minus F2. And I need all of these to calculate the geometric resistances Rij. Excuse me. Alright. F12. Direct substitution into the formula, so that I is 1, J is 2, so this is half S minus S square minus 4 times R2 by R1 square to the power 1 by 2. This is not the way you write brackets or parentheses, they have to be different, but pardon me for that, this should have been a parenthesis instead of a flower bracket. R2 and R1 are equal to 1 meter each. I need to calculate S. To calculate S, I need this capital Rj and capital Ri, and you can say those are Rj by L and Ri by L. So capital R1 is 1 by 2. Capital R2 is 1 by 2. This is R1 by L. R2 by L. Please do not confuse these with the resistances R1 and R2. They are different. Okay, these are just for plug and chug in that formula there. Unfortunately, they look the same. Then I substitute, calculate S from this information. So S is 1 plus Rj square. So J is 2 for us. So this is 1 by 2 square divided by Ri square, 1 by 2 square. That's 1 plus 1/4 is 5/4, by 1/4 is 5, 5 plus 1 is 6, so S is 6. Once I calculate S, substitute. Okay? So F12 is 1 by 2, 6 minus 4 times R2 by R1, which is 1 square, bracket close. And that's 6 square, I'm sorry. If you get an imaginary number, then you're doing something wrong here. Okay? So 6 square is 36, 36 minus 4 is 32, square root of 32 is 5.6, 5.8, something like that. So F12, substitute and solve. 0.17 for recall. 0.1716. I realize these are boring details, but I want to do justice to this problem by calculating each one of them. Okay? F21 times A2 is F12 times A1 by reciprocity. A1 and A2 are the same because they have the same radius, so good news. F12 is equal to F21, so I don't need to go ahead and calculate F21 using this formula, but in case that this was a conical tank of some kind, then the top surface and the bottom surface will not be the same. So that's an idea for an example. So you have to do this calculation twice. Okay. Depends on your SEIs, yeah. All right. Thankfully, we don't read the SEIs before the final exams. Otherwise, it's bound to be backlash. Not from my side, but human beings are human beings, right? People's feelings get hurt no matter who you are. So people will do foolish things when they're in a cornered position. All right. So now, moving on. I need to calculate F23 and F13, right? So F23 is 1 minus F21, and F21 is the same as F12, so this is 1 minus 0.1716.8284, I believe, somewhere here. I misplaced the sheet, but should be 0.8284. Okay, and then same idea. I need F13. 1 minus F12. Same. 0.8284. Okay, we have all the view factors calculated. This is tedious work, as I said, but it is necessary. Once I do that, I can calculate all the resistances. So I can calculate R12. So 1 by A1 F12. Is it okay with everybody if I don't write the details of all of these things? A1 is known, F12 is also known. So substitute. And maybe just to be clear, A1 is equal to A2 is 5 times 1 square, so many meters square. So this is equal to the following. .85 per meter square. Make sure that you're doing it as 1 by A1 F12. I have commonly seen people making the common error. They will just calculate A1 F12 and write that as the answer here. Okay, so please make sure you're doing it as a reciprocal. Okay, and then likewise R13 A1 F13. If it fancies you, you can also say this is 1 by A3 F31. But who wants to calculate A3, right? Because surface area of a circle is much easier, so I'll just stick with 1 by A1 F13. This will end up being the same thing, or maybe slightly different. F13 is different, so this is 0.38 per meter square. And the last one, I'm going to sneak it down there. That's R23. This is 1 by A2 F23, or 1 by A3 F32 if you want, if you have the information. The reciprocity rule always applies. This is also 0.38 per meter square. All right. So we have everything good to go now. We have the resistances calculated. We have the network drawn. All I have to do is apply Kirchhoff's laws for electrical networks. We have already applied Kirchhoff's law for radiative systems by saying, okay, diffuse gray surface epsilon and alpha are the same. And based on that is actually how we came up with this resistance network. And it's really a thing of beauty that Kirchhoff came up with the electrical network idea. His laws resulted in the thermal network idea as well. And there is this confluence of these two disparate ideas into one nice tool for us as engineers. Okay? Alright. I'm going to redraw the network here, you don't need to. This is sigma T1 to the power 4, T2 to the power 4. This is J3, J1, J2. And I have R1, R2 and so on, which we have already calculated. So R1, R2, R12, R13, R23. Okay, now choose any node that you want. Typically you want to choose a node where information is available, so I start off with node 1 because I know that the temperature there is known to me. I could as easily start with node 2 as well, EB2 or sigma T to the power 4 because that temperature is also known. But I'm going to go from the higher to the lower temperature, which is the direction of heat flow, right? So start here. This is labeled as Q1. Think of that as a current. It's going to come to this junction here, which means that it's going to split into two branches. Okay, so I'm going to have one flowing here, one flowing here. So this is Q13, this is Q1, and this is Q12. Is everybody able to see my writing on the board? People in the back? Everything clear? Okay. Alright. And then I have Q23. Obviously the current has to flow here. So this is Q23. And you see now we can translate this into a nice resistance network by saying, okay, current starts by flowing into this node as Q1, flowing through this node as Q1, comes to this junction here, it splits into two branches. Watch this. This current will come to this node, but there is nothing going on there, so the same current will flow through here as well. So Q23 is the same as Q13, which means that those two resistances are in series. Okay, that's one good news. Then I also have that Q1 is Q13 plus Q12. And then all the little tributaries come back together, join the ocean. So I have Q1 flowing back in here. This is Q1. Look at this. Previous circuit that I had drawn, I had marked Q2 flowing the other way. Which tells me that Q2 is the opposite of Q2. Okay? So Q2 is minus Q1. Now we draw it in a much more simpler manner. And I'm going to clear up this panel here so everybody's done with it. This is kind of odd to look at because it's triangular and so on, so we will just draw it as horizontal and vertical things. Sigma T1 to the power 4 J1. Okay, this is resistance R1. Current flows from sigma T1 to the power 4, goes through J1, splits into two. So I'm going to have but I see that one of the branches is flowing through, the current in one branch is the same as the current in the other one, so I'm just going to join them together as series resistances. They combine. This is J2, T2 to the power 4, this is R2. Then on the top I have R13 and then I have R23. And I have R12 here. Does this make sense to everybody? The way the network has been drawn. It is exactly the same thing as that odd shaped thing there. I have Q1 coming through. Splits into Q12, Q13, which is the same as Q23. All of them combine together and go into Q1. I need to calculate Q1, which is the first part of the problem. So this is just taking that series, adding them together, then I have a set of resistances in parallel. I use the parallel law of reciprocal law for the parallel resistances, and then combine everything into the total resistance. So if I draw it out, this is what is going to happen. So Q1 is going to be sigma T1 to the power 4, sigma T2 to the power 4 by R total, where R total is the net resistance through the network. Is R1 first of all, this one. Reduce all of these to a single resistance that's going to be in series with R1 and series with R2. So this is going to be the following: plus 1 divided by R12 and that's 1 by parallel, right? So that's R13 and R12, and then the sum of those two and reciprocal of that. So that's 1 by R12 plus R13, R23, the inverse, plus R2. Does this make sense to everybody? These are added first, then that combination is combined with this in parallel, reciprocal rule. I have to take the inverse of that to get the resistance of that parallel network, which is the second piece. Substitute all the numbers. Our total ends up being the following. It's 1.49 per meter square. Substitute for T1 and T2. And so Q13 is going to end up being 13 kilowatts. Okay, after everything has been substituted. T1 is 800 Kelvin, T2 is 500 Kelvin. If they are not given in Kelvin, convert them into Kelvin. Sigma is known to us, and we're done with this part of the problem. Then comes the painful part of the problem. We need to calculate T3. Thinking I'll keep this one. Once again, several ways to do this. Okay, this is just taking an electrical network and then figuring out, okay, what is the voltage at one of the nodes. The way I approach it is using the following ideas. I know that Q13 is the same as Q23. Which tells me that J1 minus J3 divided by R13 is the same as J1 minus J3 minus J2 by R23. And I believe R13 and 23 were the same values, if I'm not wrong, and they are right. So we found out which means that I can actually solve for J3. J3 is nothing but J1 plus J2 by R13, which is sigma T3 to the power 4 is Does this make sense to everybody? Once again, multiple ways to solve this. This is just one particular way. Okay? Which means that to find T3, I need J1 and J2. Right? So how do I find J1 and J2? I'm going to erase this figure here. And to find J1, look at this. Focus on where J1 is, right here. I know R1, I know T1, I know Q1, because we just found out Q1. So I can find J1 using the following idea. Okay, so I have sigma T1 to the power 4 minus J1 by R1 is equal to Q1, which tells me that J1 is sigma Q1 is 13 kilowatts, R1 is known, T1 is 800 Kelvin. Crank up the numbers, this is what you end up getting. So J1 is 16.96 kilowatts per meter square. Make sense to everybody? J2. Be careful. Q1. If you look at where J2 is sitting, is flowing from J2 to sigma to T2 to the power 4. So which means when you are writing the current as the potential difference divided by the resistance, you have to do the following for J2. J2 minus sigma T2 to the power 4 by R2 is equal to Q1, or this is equal to minus Q2, which I don't know, but I know Q1. So you can ignore this minus Q2 part, which tells me that J2 can be calculated. J2 is sigma T2 to the power 4 plus Q1 R2. All of these are known to us. Solve for J2 is 9.81 meters per second square. Okay. Eventually I combine everything together and write J3, which is sigma T3 to the power 4, so substitute. It's 9.81 and then that's 16.96 divided by, I believe R13 was 0.38. Okay, look at the units. So this is kilowatts per meter square. This is 1 by meters square. Okay, then solve for T3 and Kelvin. Ends up being approximately 697 Kelvin. Okay. So that's the entire problem for us. Yes, this question.
When you box J3, shouldn't that be J1 over J2, J1 plus J2 over 2? Because your R's cancel on right above that, and then you have 2 J3 on the right side.
Oh, yes, yes. So there's a factor of 2 there.
But the R13 shouldn't be.
Oh, R13 and R23 are the same, right? So if I, let's see. So let's do this. From here, J23 times 2 by R23 is J1 plus J2 by R23. So you're right. There should be no R13. There should just be a factor of 2. Thank you. And so that's why these units, I was a little suspicious.
Yeah.
So they should just be 2. Now it should work out. Because there is no area here, so this has to be the flux. Okay. And epsilon is equal to, I guess epsilon doesn't come into play here anyways. you're looking at the ideal body emissive power or emissive flux. Okay. So this answer is still right, but thank you for pointing it out. Alright, so we have completed this problem in its entirety, including all the steps. I want to see if there are any questions on how we accomplish this problem. As always with any radiative resistance problem, you start off by looking at information given, you draw the resistance network. Some of the nodes might cancel off, some of the resistances might cancel off. Once you do that, you go through all of these characters here, the surface resistances, which are R1, R2 and R3. Then the geometric resistances, which are the Rij's, R12, R23 and R13. Once you do all those calculations, it is just an application of Kirchhoff's current laws. Pure manipulation, that's all it is. Okay? Alright. Last questions on radiation. That ship is sailing soon. We spent a good amount of time on radiation because this is the most interesting, in my opinion, and the least intuitive of all of these heat transfer modes. Conduction is fairly trivial. Okay, there is steady conduction with heat generation, without heat generation. Transient conduction is not easy, but we just only do a zero-dimensional transient conduction. Even though I did show you the equations for 1D transient conduction, okay, the heat equation. Convection, in my opinion, is perhaps the most complicated of the lot because of the fact that it's an interaction between two different types of surfaces. It's a solid-fluid interaction, and when solids and fluids interact, anything can go wrong. Many things can go wrong, and mostly they will go wrong. Okay? And that's why convection is really complicated. And I spent a good portion of my life doing convective heat transfer. My problem was more on the characterization of heat transfer between a gear tooth and a fluid film coating it. So in gears, radiative heat transfer is also present because the gears can get pretty hot when you're running. And in the absence of oil, things can go berserk. But convection is much more complicated because of the curved nature of the gear teeth and also the thickness of the fluid layer on the gear teeth. It's not like it's immersed in a bath. It is just a thin layer of oil on top of it. Okay, so much more complicated problem, and there are not many solutions available. The aim is to cool substances. That's the aim of using lubricants in transmissions. And my whole study was based on how this cooling takes place. So convection has a special place in my heart. And that said, I hope I will not make it as miserable as radiation. So next, 8 lectures on convection. Very brief recap of conduction and radiation. Conduction takes place due to molecular diffusion. Or due to lattice vibrations in solids, if you like. Phonon transfer, that's called phonon transfer. The words are not important. Diffusion, molecular diffusion is the main thing. It takes place in the absence of bulk motion. Obviously, it's taking place through a solid or a liquid or a gas. It means that it requires a medium. And we have fairly thoroughly investigated conduction heat transfer. The tools that we used were Fourier's law of heat transfer, which is phenomenological, it's experimental based. And we also looked at the heat diffusion equation. In planar systems, we looked at it for polar systems as well. Okay. Radiation heat transfer, much more physics based in some sense. And this is going to take place as a presence of the temperature of the body. Okay. So this is due to vibrations of the atoms as a consequence of the internal energy of the body, or as a consequence of the temperature, due to temperature. capital T, temperature. There is no need for any medium present for radiation. It's best if there is no medium at all. Radiation is complicated with the fact that it's both spectral and directional. It's a function of wavelength, it's a function of direction as well. And we had a host of equations to characterize radiation. Most predominantly the Planck distribution, which helps us characterize the intensity of ideal bodies. Then we have Kirchhoff's laws, which helps us understand, okay, when can absorptivity and emissivity be equal to each other, which will simplify our analysis. In the process, we come up with this network idea for resistance, radiation problems. So we've done these two pretty thoroughly, in my opinion. We've solved a good amount of problems as well. Now we move to convection heat transfer, where fluid contact required. That's the first thing. The second thing for convection heat transfer, obviously because the fluid and the solid are contacting with each other, takes place in the presence of a medium. That is goes without saying. The second thing is it requires bulk motion. This bulk motion can be a natural bulk motion due to the buoyancy effects, due to the density changes, variations in temperature, or this can be forced bulk motion if you take a fan and you blow it across the surface. So there is forced convection and natural convection. Okay, let's take a thought experiment. Okay? So, hot plate, cold plate. And in between I have a stationary medium. What are the modes of heat transfer between the top and the bottom? What are the modes of heat transfer between the top and the bottom surface? There is always radiation, absolutely. So there is radiation. What else is there? Conduction, because there is a temperature gradient, so there is Q conduction. Now let's do the following. Flip it up. What are the modes of heat transfer now? And be careful. I'll tell you there is always radiation, so I'll write that thing down. Is there conduction taking place? And this is stationary fluid, let's say, to begin with. Okay, so stationary, I should qualify, okay, this is also stationary fluid. Now, is there conduction or convection taking place across the stationary fluid? Any guesses?
Convection.
Convection is a good guess. Why? Yes?
As the, like, well, I guess this implies motion, but as the bottom surface is heated, its density becomes lesser than that on top, so
Absolutely, absolutely, fantastic. So there is going to be a bulk motion created due to the molecules, even though there is no forced heat transfer taking, there is no forcing of the bulk motion, there is bulk motion due to natural consequences, because the fluid molecules here get heated up, they become lighter, so they start going up to the top, displacing the heavier ones on the top which come to the bottom, and so this creates a convective current. So there is convection here. Now, I'm going to take the same situation hot and cold, and there is fluid here. And if I want to characterize forced convection, I can think of it as doing the following. I take a small syringe, and then I take a molecule of hot liquid from there, I transfer it here. I take a small syringe, I take a molecule from here, I transfer it here, I transfer it there. And so you see that if I had the situation of forced convection, the rate of heat transfer is going to be much higher than if I had the state of conduction. Okay? And eventually, what can be shown, and we will be seeing it as we solve problems and so on, conduction is nothing but the limiting case of convection. So, as the amount of bulk motion becomes smaller and smaller and smaller, the convective heat transfer coalesces together to become conduction heat transfer. Okay, so in this case, I'm going to have forced convection plus radiation. And remember, convection is always conduction plus diffusion, advection. Okay, so when you say convection, it is implied that at the first